Okay, thanks. Can everyone hear me okay in the back? Everyone good? Okay. So let me start by thanking Peter Vickers for organizing the event. It was a really wonderful day yesterday, and I'm just really thrilled to be here and happy to be a part of the workshop. You'll see my talk this morning is going to focus on sort of a mistake that I made. I'm going to do a little bit of error analysis, which, you know, scientists, if they make a prediction that comes out badly, that's sort of the first thing they do is back to the drawing board, sort of what happened here, what went wrong. And I'm going to try and do something analogous to that as a philosopher who made what turned out to be a mistaken call about some science that I think is pretty interesting. I'm going to go back and try to look at sort of what happened here. So to start with this, so the general issue here is the colors of the dinosaurs. And I just want to begin by giving you a sort of feel for what was until recently the sort of state of play on this question. So I'm just going to, as an example, just pick out a favorite of mine, Corythosaurus, this one of the hadrosaurine, one of the lambeosaurine duckbill dinosaurs. This is what he looks like, or she, with the sort of crest on top of the head. And you see, you know, in popular dinosaur books, these are images I'll show you here, just some things I found on the internet. You know, you get all kinds of color representations here. This is kind of looks like plumage of some kind of bird or something, but the face is kind of drab and gray. Here's another sort of not so well done one with the blue crest on top, right? You get sort of also they're really going for the colored crest. That seems to be a theme. That's an interesting one. I'm not sure what's going on there. Here's an interesting one where it's just kind of drab gray, but with the neon blue crest. You get some tiger stripes or zebra stripes in there every once in a while. That one, I don't know. Maybe it looks like a goldfinch or something. I'm not sure what's going on. Zebra stripes, but with still the colored crest. And then there's this one, which I found, which just seems quite fanciful. I'm not sure what it's about. So you'll see, you know, if you pop open children's dinosaur books, or you know, look at representations in film and television, and even in books by scientists that are meant to be quite informative, you see all kinds of artwork, all kinds of representations of the colors of the dinosaurs, and they're really all over the place. Most of this is pretty speculative, almost all of it. Until very recently, and I'll talk about how things have changed, these speculations are all based on pretty loose analogies with living organisms. So you'll sometimes, especially in earlier work, you'll see scientists say, well, you know, maybe there's some sexual selection going on that explains why the duck-billed dinosaurs had those crests. And, you know, maybe if it's sexual selection, maybe, you know, that the coloration would be something like the plumage of modern birds, or you know, large mammal herbivores, elephants, rhinos, usually have drab coloration, so maybe big dinosaur herbivores would have similar coloration. You get that kind of thought. And then you get analogies with zebras, or, you know, carnivores, tigers have stripes, and other cats have spots. You get these just kind of loose analogical reasoning that's largely unconstrained by any, you know, serious empirical evidence. Just kind of suggestive analogies. That's what you get. Before I say anything more, I want to issue one word of caution about the topic in general. Throughout the talk today, I'm going to be talking about dinosaur science, which I think is really interesting, and I do hope to draw some connections to the realism debate in the second half of the talk in particular. But I want to really emphasize that for many paleontologists working today, dinosaur science is not really where the action is. It is kind of a lively area of work, but its profile, its public profile is a lot higher than I think many paleontologists think is probably warranted. And there's a simple reason for that, which is that many paleontologists today really think of themselves as trying to learn something about evolution, and they want to try to study patterns and trends in the fossil record and then draw some conclusions about underlying evolutionary processes that gave rise to those trends. To do that, you need good data. You need really large sample sizes. You need to look at big collections of fossils. So now they use databases with thousands and thousands of fossil specimens entered into the databases, and they sort of crunch the numbers in a lot of the studies that are done today. I think a lot of paleontologists think of kind of dinosaurology as being plagued by bad data. They're just, we don't have enough specimens to look at to really draw the kind of conclusions about evolution that you'd want. Where you really should be looking is, you should be looking at the marine invertebrate record. That's really where a lot of scientists, I think, would say the action is in the last 20 or 30 years, if not a little bit longer. And so I just want to kind of make that point to kind of put the rest of the talk in context. We're really looking at a small bit of paleontology that's not really the main thing. And I want to make a quick shout out here to David Sepkoski. If you're interested in getting a really nice picture of the current state of play in evolutionary paleobiology, Sepkoski has this new book out, Rereading the Fossil Record, with University of Chicago Press. It's a fantastic book. He's a historian of science who has taken it upon himself to chronicle the last couple of decades of work in paleobiology, and it's really, really great stuff. And I think in the kind of scientific work that David is writing about evolutionary paleobiology, I think there are a lot of other questions that are relevant to the realism debate as well. In this talk today, I'm just not going to focus much on that. So quick outline. I'm going to begin with, this talk is a little bit more autobiographical than it probably should be, or than I'm used to. There's a little more autobiography than I'm used to giving in talks like this, but because the idea is to describe this sort of mistaken prediction I made and then draw some lessons from it, I am going to have to kind of start with some background here. So I'm going to begin by providing some context and say a bit about this debate I was having with a colleague, Carol Cleland, at the University of Colorado a few years back, kind of running conversation that Carol and I were having about historical science. And then I'm going to say a bit about the science and talk about why or how it is that it turns out I lost this bet that I made against dinosaur science. And then I'm going to, in the second half of the talk, try to draw some conclusions and sort of ask, first of all, well, what does the fact that I got this issue wrong mean for the debate that Carol and I were having earlier on, which provided the context for my making this prediction about where the science would go in the first place. And then secondly, I'll look at some possible consequences for the realism debate. It's really the last, I have to confess, the last part of the talk, I'm kind of in the process of thinking through, and so I'm very open to suggestions on this. I have a few ideas. I'll try to develop a bit of an argument, but this is a little bit untested here, this last section. So to start with the first part, there's a nice picture of Carol. Carol Cleland published this paper in Philosophy of Science in 2002. It's a paper, I've talked to people who think there are problems with her work on this. I really like this paper, and it's had a big influence on my own thinking about historical science. There's some, although I initially disagreed with her, there's a lot in this paper that I really admire. So I'm going to begin by just sketching some of Carol's view on this. In this paper, it's called Methodological and Epistemic Differences Between Historical Science and Experimental Science. She identifies these two kinds of science, two ways of doing science. She treats them as ideal types. So she acknowledges that if you look at any particular scientific episode, you might find, in fact, you quite likely will find that it's kind of experimental, kind of historical. But she still thinks if you look at scientific practice, you can find these two types of science. And they're distinguished from each other in two ways. So on the one hand, they have different sorts of target hypotheses. So classical experimental scientists are typically interested in regularities among event types. They're interested in patterns. They're interested in maybe laws, laws of nature. Prototypical historical science they're interested in testing target hypotheses about token events in the past. Gesundheit. This is just the difference here is between really particular claims and general claims. Experimental scientists are interested in generalities. Historical scientists are interested in particularities. If you just focused on this first line of the table, Cleland's view isn't really saying much that's very new. This is an old distinction. It goes back at least, probably goes back much further than this, but it goes back at least to the late 19th century. Neo-Kantian philosophers, Windelband and Rickert and people like that drew a distinction between ideographic and nomothetic science. And so if you focus here, really all she's talking about is nomothetic versus ideographic science. That's the basic idea. But she goes a bit further and identifies two different styles or modes of empirical testing, or two ways of confirming or disconfirming the target hypotheses, which she thinks are appropriate to the two different kinds of science. So experimentalists, this is sort of basic stuff. They intervene on one variable while holding others fixed. They do repeated trials, trying to rule out false positives and negatives. Won't worry so much about her characterization of experimental science. The thing we'll really focus on here is her treatment of historical science. In her view, historical scientists, they start out with a set of observable traces. They formulate hypotheses which would, if true, explain the traces they're looking at. And then they set out to look for what she calls a smoking gun. She loves this term, smoking gun. It's really kind of the heart of her account of confirmation in historical science. A smoking gun is just a trace or a collection of traces that enables scientists to discriminate among the rival hypotheses they've generated. So it's a trace or set of traces that, let's say, is explained by one of the rival hypotheses but not by the other, for example. So one example of this that she has given in a couple of different papers is the discovery of iridium and shocked quartz at the boundary, in the boundary clay between the Cretaceous and Tertiary rocks. Together, those traces seem like a smoking gun for an asteroid impact 65 million years ago. And that played a crucial role in the kind of work on the end Cretaceous extinctions in the 80s. So it's just a nice kind of simple example of a smoking gun. I was really excited yesterday in some of the talks to see that some of the episodes of science that were being discussed really fell neatly into both of these categories. So some of the examples of cosmology, I think, fall nicely within the category of historical science. Some of the other examples we saw yesterday involved experimental traditions in physics, which clearly fall over here. So, oh, there's a smoking gun. Oops, sorry. Concern about Cleland's view. This is a more recent concern that I have, and I've become convinced. Basically, the more I learn about paleontology, the more I talk with people like David Sepkoski and learn what's really going on in the science, the more I've come to think, well, there's an awful lot of work in paleontology that really doesn't fit Cleland's description of historical science very well. And I'll just give two examples. The first one is actually an example of computer modeling. In the early 70s, there was a group of scientists, including some big names. Stephen Jay Gould was one of them, David Ropp, the guy who later became famous for working on extinction, and a couple of others got together at the Marine Biological Lab in Massachusetts, in Woods Hole. And they designed the first computer simulation of large-scale evolutionary processes that became known as the MBL model. And it was basically a stochastic model that represented, you start out with a lineage, and with each time interval, the lineage has a certain probability of going extinct or persisting with no change or branching, speciating. And they found they could represent macroevolution with this computer model. And the one really interesting thing about it is natural selection played no role in the model anywhere. And the patterns they generated with the model actually looked a little bit like some of the actual patterns you see in the fossil record. It was a really interesting moment in the history of recent paleontology that Sepkoski writes about quite a lot in his book. And it was modeling. And modeling doesn't really figure into Cleland's picture of historical science at all. And I've come to think that's a real sort of problem for her. I think a lot of historical science does fit her description quite well. It really does look like a search for a smoking gun, but there's some things that don't. Another thing, fossil crunching is a term that Michael Ruse introduced in his book, Mystery of Mysteries. He has a chapter on this paleontologist from the University of Chicago, Jack Sepkoski, who, this is just a kind of irrelevant detail. He happens to be the father of David Sepkoski, the historian I've been referring to. Sepkoski started using huge databases of fossil specimens and then used pretty sophisticated statistical techniques to identify patterns in the data that he was looking at in these databases to try to just find patterns, say, of biodiversity change in the fossil record. Is one issue he's famous for working on. This is another kind of thing where if you start doing large-scale statistical studies on big samples of fossils, you're working now with big data. There's not any particular fossil find that's going to serve as a smoking gun for any hypothesis you're interested in. Kind of by definition, you're looking for patterns that show up in a very large sample. So it doesn't really, I don't think it really fits the picture of the search for the smoking gun all that well. But I'm not, so having said that though, I'm not going to really develop this concern very much. We'll set that to one side. I want to talk a little bit about the actual argument that Cleland makes. She borrows an idea from David Lewis called the time asymmetry of overdetermination. And so causal overdetermination is what you have, for example, in a firing squad where you've got a bunch of shooters and any one bullet would be sufficient to kill the convict, but in fact you have a sort of overkill situation. There's more causes than you need to bring about the effect, I guess is one way to think about it. And Lewis suggested, if you go back and look at his original paper, it's a little bit tough to tell what he actually thinks about this. He never quite asserts that there's a time asymmetry of overdetermination, but he's kind of floating the idea, exploring the idea. And the thought here is that upstream causes seldom overdetermine their downstream effects. So things like firing squads are quite rare. That's a case where upstream causes do overdetermine the downstream effects, but that doesn't happen very often in nature. The flip side of this is that downstream effects usually overdetermine their upstream causes. Okay, so there's a kind of time asymmetry here that Lewis is interested in. Now, Cleland takes this and really runs with it. And well, I'll just read this. This is a bit from her 2002 paper. And she still thinks this. She has a recent paper in the British Journal for Philosophy of Science where she kind of follows up on some of these themes. Because of the asymmetry of overdetermination, there are usually an enormous number of subcollections of the effects of a past event that are individually sufficient, given the right theoretical assumptions, to infer its occurrence. The trick is finding them. So she thinks that, oh, is this in the way?
If you're not using it.
Oh, no, go ahead. So she thinks that Lewis's notion of the time asymmetry of overdetermination supports a kind of optimism about historical science, that it guarantees that those traces that we need, the proverbial smoking guns, are going to be out there to be found. That's sort of her take on this. She's quite optimistic. The overdetermination of the past by the localized present provides the rationale for this work, the search for the smoking gun, ensuring that the probability of finding such traces is fairly high. Okay, this is her kind of optimistic epistemology of historical science. And when I first saw the 2002 paper of hers, I reacted kind of negatively to this. This seemed to me to not to follow actually from Lewis's notion of the time asymmetry of overdetermination. And so my initial reply to Carol's work here was to say, well, we actually know, this is kind of old news in the historical sciences. We know that historical processes often degrade or destroy information about the past. So paleontologists, for example, routinely talk about the incompleteness of the fossil record. There are many different respects in which the record is incomplete. They actually study sampling biases in the fossil record. Even going back to Darwin, when Darwin lamented the incompleteness of the fossil record, this has been a real theme in historical science, the degradation of information about the past. And so my thinking was, well, given that historical processes often destroy information about the past, and we know this based on our background theories of taphonomy, the fossilization process, and so on, it seems plausible that local underdetermination problems would be quite common in historical natural science, even in spite of the time asymmetry of overdetermination. It's sort of my thinking on this. Maybe a lot of those downstream traces are just getting destroyed or degraded to the point where we're no longer able to interpret them as evidence of earlier events. So to develop this response, I introduced a couple of lines of argument, neither of which worked out too well. I now have sorry, I have reservations about both lines of argument, which I'll say a bit about as we go along. Reservation about one of these lines of arguments is the main theme of the talk here. So first, I tried to give some compelling examples of local underdetermination problems in historical science, just to make it plausible that they're especially widespread. And then I tried to argue that there's a difference here between historical and experimental science with respect to the role played by background theories. In my mind, I was thinking, well, in historical science, background theories in geology and taphonomy often tell us how evidence gets destroyed. In experimental science, background theories often tell us how to create new evidence, or how to design systems in the lab that enable us to kind of manufacture new effects or what have you. And that struck me as an interesting difference that's relevant here. I had to add this more. This might be actually this could be a really important slide. In the course of preparing this talk, another potential problem with Cleland's view actually occurred to me, which is somewhat unrelated to the rest of the stuff I'm going to talk about today. But I think it's so interesting that I just felt like I had to insert it. This is not an argument I developed when I first responded to her work, but it's something that's occurred to me quite recently. She makes a big deal of the fact, she claims that the time asymmetry of overdetermination is not something, it's not a bit of metaphysics, it's not knowable a priori. Instead, she thinks of it as an empirical scientific claim about the universe we live in, and she she explores some associations, some possible connections between this idea and thermodynamics and things like that. She really sees this as a sort of a scientific view about the universe. She wants not to be doing armchair metaphysics, basically. One question I have about this, though, is which type of science, historical or experimental, is the one that supplies the evidence for the time asymmetry of overdetermination? And I think there's some potential to create a dilemma here for her view. If it's experimental science that supports the time asymmetry of overdetermination, then she's in the position of saying that historical inferences are warranted because of this thing that we know of owing to experimental science. So the epistemology of historical science is kind of rooted in the findings of experimental science, which would be kind of a weird view. If she says, well, it's historical work that shows this, which seems actually prima facie less plausible to me, but if that were the claim, then it seems like there's a circularity problem that historical work is helping us to establish this time asymmetry claim, which then provides the warrant for further historical inferences. So I think either way, it's going to be a little bit awkward here. This is just another issue that's occurred to me. Okay, so in going back now to my initial response to some of Cleland's work, thinking about what local underdetermination might mean, I was trying to draw a distinction between local and global underdetermination, just to give a couple of examples. In historical science, global underdetermination would be really a kind of radical, skeptical problem. You know, how do we know the world didn't pop into existence 5 minutes ago? Local underdetermination is going to be sort of a category of cases where you have hypotheses about localized historical events that are underdetermined by the available evidence. That's sort of the rough idea. And then in this earlier work, I gave this account of what a local underdetermination problem looks like. Two hypotheses have got to be genuine rivals. They've got to be equally well supported by the available evidence. They have to have roughly equal helpings of theoretical virtues. They got to be comparably, they have to have comparable explanatory power, or comparable, simplicity, or whatever the virtues are that you might like to mention. And then this is the important one. Background information, background theories have to give us some reason to think that the two hypotheses are also strongly empirically equivalent, which is to say, our background knowledge has to give us some reason to think that as future evidence comes in, it's not going to help break the evidential tie. Okay, this is the condition that kind of got me into trouble a little bit earlier. Okay, so just a quick observation about this. That last condition, D, it does not say that the two hypotheses are in fact strongly empirically equivalent. It's weaker than that. It only says that we have good reason to think they are. The background theories that are available give us some good reason to think they are. And that implies that something which is a local underdetermination problem at an earlier time could cease to be one if unexpected new evidence comes in. This is actually an implication of that analysis that I gave earlier on that I don't think I quite appreciated when I first gave the analysis. It's an implication that's been driven home to me by subsequent developments. Okay, so in this earlier work, as I mentioned a minute ago, I tried to kind of make compelling the idea that local underdetermination is especially widespread in historical science just by giving some examples. And one of the examples was the colors of the dinosaurs. I mean, just thinking about it, didn't seem to me that we have any reason to think that we'll ever have any evidence to discriminate among the hypotheses that are represented by these sorts of reconstructions. And I made this point in this earlier paper by reference to this particular dinosaur, Pachycephalosaurus. Not the same one as what I just showed, but another one where if you look at representations, you see the colored head and stuff. Anyone can see that the hypothesis that Pachycephalosaurus had a neon blue patch on its head is strongly empirically equivalent to the hypothesis that it had a neon green patch. We have good reason to think this because we know that information about coloration is destroyed by the fossilization process. Okay. So my take on this was it's just an example of an issue and a question in historical science. What color were the dinosaurs that we're just not ever going to know the answers to? But it turns out I was kind of wrong about that. So moving on to the next bit of the talk. In 2010, so this debate that I was having with Cleland was taking place around 04, 05, 06, 07. Around 2010, this paper gets published in Nature by an international team of scientists. It included some Chinese scientists because the specimens they were looking at had been gathered in northern China, and also some British scientists from, I believe on this first paper, Michael Benton at University of Bristol was one of the co-authors, and he's very interested in this kind of work. They realized that you can draw some inferences about coloration by using a scanning electron microscope to look at melanosomes. And melanosomes are these tiny organelles that are inside cells of feathers and feathers and skin tissue. And they're the organelles that house pigments. So we have melanosomes in our skin tissue. Living birds have them in their feathers and so on. Well, it turns out dinosaurs had them in their feathers too. And you can look at them and you can look at the shape. They come in different varieties. Some are more cylindrical, some are more spherical. You can look at how densely packed they are. And you can draw some conclusions about coloration, mainly by comparing them to the kind of varieties and packing structures of melanosomes in modern birds. That's the main approach here. And that's a nice image of what melanosomes look like. So this first paper, Zhang et al., they looked at melanosomes from a number of different specimens. One was an ancient bird, one was this dinosaur, Sinosauropteryx, one was an isolated feather, they didn't know what it belonged to. There were a number of specimens they looked at. But the most dramatic finding was probably this Sinosauropteryx finding. They say only phaeomelanosomes, this is just one variety of melanosome, have been identified so far in filaments from the tail of Sinosauropteryx. And this suggests that the dark colored stripes along the tail in the fossil and possibly also the filamentous crest along the back exhibited chestnut to rufous reddish brown tones. So we now have good empirical evidence that this creature had reddish brown stripes on its tail, because they found in the feathers of the tail, they found bands of tissue with these melanosomes, and then bands with none, and then bands with melanosomes and bands with none. Really interesting work. Okay. There's a second study came out very shortly after, a couple months later, in Science, by a different team. This included also a number of Chinese scientists and then some scientists from, I think, from Yale University. And they looked at just one animal, Anchiornis, which is another small theropod dinosaur from the Jurassic, I guess. They went a little bit further in terms of their claims about coloration. And this is actually a picture that they published in their paper, a little artistic representation of what they think the animal looks like now based on their work on melanosomes. It's really fascinating. And they gave this vivid description in the abstract. I love this. Quantitative comparisons with melanosome shape and density and extant feathers indicate the body was gray and dark and the face had rufous speckles. The crown was rufous and the long limb feathers were white with distal black spangles. I guess, I don't know, maybe ornithologists have technical terminology for describing these things that they're using. I don't know. I find it kind of nice. Okay. More recently, there's a scientist, a guy named Ryan Carney at Brown University, who got this isolated Archaeopteryx feather from the Solnhofen quarry in Bavaria, where they found the original Archaeopteryx specimen. And he was just set out to find out, well, what color was the iconic Archaeopteryx? He did the same sort of work in his lab and came up with the conclusion that some of the wing feathers were black. This is another just little image I found. This is highly speculative, not based on Carney's work at all. This is kind of what we were left with before the melanosome work. Now we can say with some certainty the thing had black feathers, black wing feathers. This is at the University of Bristol. Michael Benton's research group has a nice web page with some information about this work. And they say, I just love the way they put this. This is a little bit of hyperbole and a little bit of advertising for the work. They said the impossible seems to be true. Paleontologists can now tell the colors of the dinosaur feathers. Oops. Okay, so now to do a little bit of error analysis. With hindsight, I clearly got it wrong in predicting that we wouldn't be able to figure out the colors of the dinosaurs. But I still, and looking back, I'm wondering, well, was that actually a stupid thing to predict based on the evidence available at the time? I'm not sure. I think given the evidence available at the time, well, maybe, I mean, it seemed like a safe bet. This is an interesting thing to think about. When I sent this 2005 paper out, I did get an interesting comment from a referee. Well, what if they come up with some new evidence, right? But the example given was a philosopher's sort of example, like a science fiction-y one. Like, what if in the future we encounter, I kid you not, this was the example that was proposed. Well, what if we get some new evidence of dinosaur coloration? And so in my own, at the time, just to help you see what at the time in my own mind, I was like, well, this is if there were any new evidence, like it would have to be something ridiculous like this, right? So, whoops. One possibility that I take very seriously is that I just didn't know as much about the relevant work as I thought I did. You know, I had looked in a kind of amateur way from the sidelines at some of the, you know, some books. I'd done a little searching and just sources that are available. Nothing, you know, none of the work on melanosomes had been published, you know, in 04, 05, so it wasn't out there yet. But I was an outsider, still am an outsider as a philosopher, and you know, maybe I just didn't talk to the right people, or you know, maybe it seems quite likely that this work was brewing and I just didn't know about it. And in response to this, I think it's interesting to consider, just to modify the situation a bit, and just imagine, well, what if one had made the bet a few years earlier, before the work was brewing, before, you know, shortly before scientists had even really started looking at fossil microstructure at all. But it really hadn't occurred to anyone until quite recently, I think, that some of this information might be preserved in fossil microstructure. I think it really probably would have been quite rational to make this kind of bet against dinosaur science a few years earlier, even if, maybe we draw the conclusion that I should have done a little bit more homework or something. So another thing to think about is there are other problems. The scientists who first started working on this issue realized that they were going to have to make some empirical arguments to convince people that what they were looking at was really the remains of melanosomes, because bacterial remains look a lot like what you'd see under the microscope when you look at melanosomes. It's actually quite tough to tell the difference. And so in the first article by Zhang and colleagues, they spent a lot of time building the case for thinking that these are really melanosomes and not bacteria. Part of the case involves pointing out that they occur in banded patterns. If it was a bacterial contamination, there's no reason to think that you'd see them densely packed in bands in the way you do. But that's an issue, and if it had occurred to someone earlier to look at melanosomes, that would have been an empirical problem that would have seemed like a serious one, I think. Okay, so that's sort of the story about how I lost this bet. Now I want to address two questions. First, how do these new findings about melanosomes bear on the debate that Cleland and I were having? And then second, are there any broader lessons for the scientific realism debate? And my answer to the first question is that they're not as important as they might seem. And I'm going to suggest, maybe somewhat tentatively, that there are some lessons here concerning the scientific realism debate. So to start with the first issue, the consequences for the debate that Carol and I were having. You know, at first glance, this just looks like a huge victory for her view. Like, this is a smoking gun, right, for dinosaur coloration. But I'm actually, so it clearly is a smoking gun for dinosaur coloration. So this clearly is a lovely example of historical scientific confirmation as Cleland describes it. I actually do think this fits her view very, very well. What I'm less sure about is whether this finding supports her more generalized optimism about historical science. Because I'm not sure that her generalized sort of optimism, or her view that smoking guns are in general out there waiting to be found, is the sort of view that's well supported by any particular case, either by a particular case in which we dramatically find a smoking gun that we didn't expect to be there, or by a case of persisting, her generalized view wouldn't be well supported by a positive case like this, and wouldn't be undermined by any particular negative case where we fail to find a smoking gun. And in fact, Carol herself, when she defends her view, she always appeals to the asymmetry of overdetermination. She typically doesn't try to defend her view by appeal to cases like this. And I think some other things need to be borne in mind. So for one thing, even after this work, we still know like next to nothing about dinosaur coloration. I think it's really important to keep in mind. These are fascinating and dramatic findings, but they're very localized. So for example, we know nothing at this point about dinosaur skin color. That could change. There are a couple of dinosaur mummies. I was reading recently about one especially well-preserved one in North Dakota where they think there might be some information about skin microstructure. Maybe we'll get something from some of these specimens. But those specimens are rare. There are like 5 or 6 dinosaur mummies that are in good shape that we know about. So skin color, is still a mystery. It's up for debate just which dinosaurs, how many of them had feathers. It's just not clear how much information we're going to be able to get by looking at feathers. Even in the case of feathers, there are interesting gaps. Okay, so you might think that illustration of Anchiornis that was published by the scientists now represents like our knowledge of the true colors of the dinosaurs, but actually there are gaps in what we know that they filled in speculatively. They didn't have any tail feathers from the specimen, so they don't know anything about the tail feather color. And if you look back at the photograph or the artistic rendering, you'll see the tail feathers were kind of charcoal gray. We just don't know. And so parts of the picture that we're getting now are just as speculative as they ever were. And there are other things, sexual dimorphism. Are we looking at male or female specimens? Developmental incompleteness. Are we looking at adults or juveniles? Do the colors change over the course of development? There are a lot of questions here that we don't have answers to, and I think you could point to certainly some of these as pretty plausible examples of local underdetermination problems if you wanted to. But the deep reason why I've become convinced that the findings don't really matter that much for the earlier debate is I think the whole debate that Carol and I were having was kind of framed in a way that's not quite right. So the issue that we were disagreeing about is how much information is preserved versus destroyed by historical processes. She was appealing to the time asymmetry of overdetermination to try to make the case that information is typically preserved. And I was appealing to stuff we know about the incompleteness of the fossil record and the fossilization process and other geological processes to try to argue that information is typically destroyed. But the problem with what both of us were saying is that it's an empirical issue, just how much information is preserved or destroyed. It's a problem for historical science itself. In fact, paleontologists work on this issue. You can find papers where the whole point is to try to assess the relative completeness or incompleteness of the record for a particular clade, a particular time frame, right? So this is a problem. This is a scientific problem, really, that isn't well addressed by thinking in this kind of general way from the armchair. It's not well addressed by looking at a few examples in the way that I was trying to do. And because it's an empirical issue, I'm also kind of skeptical that appeals either on Cleland's part to the time asymmetry of overdetermination or on my part to his intuitions about the different roles that background theories play in historical versus experimental science will help very much. So now to to move on to the last part, and a part that may be most interesting for this group, but which sadly in my own mind is kind of the least developed, to think about some consequences for the realism debate. So what take-home messages might one get from this, or what what conclusions might one be tempted to draw from this kind of blown prediction about where the science would go? Well, one thing you might do is say, okay, well, lesson learned, not going to place any bets on science anymore, right? This is just not a terribly good idea. Science can and will surprise you. Such bets can come out wrong even when they seem very safe, given the available evidence. And I have to say, in my own mind, one reason why I was really keen on working through some of this stuff is because I actually do think that this misplaced bet that I made was in some ways made under ideal circumstances. It seemed like such an easy case. The background theories are easy to understand. It's only one case. You don't have to study a large number of different cases or develop expertise on a bunch of different issues. There's, a couple of centuries of fossil collecting and studying behind us with no indication anywhere in any of that, that we'd ever get information about. It just seems so easy, right? Okay. So the thought here is, well, and if you get it wrong in the easiest possible case, then, don't make the bets at all, okay? But then I started thinking, well, the problem is that no betting policy might go a little bit too far, because I think when you construe the positions in a certain way, it turns out both realists and anti-realists are in the business of making bets about the fate of current scientific theories. And so I think this is a slightly different way of thinking about realism and anti-realism than is common, but I think it's a fair way to think about it, and I find myself now torn about which direction to go in, as I'll say more about here in a minute. So starting with realism, realists bet that different versions of realism are going to kind of put this in different ways, but they bet that our best current theories will be vindicated by future evidence as it comes in. Or selective realists might bet that the parts of our best current theories whose truth would explain their empirical success will be vindicated as new evidence comes in. Structural realists might say, well, the structure of our best current theories will carry over through future theoretical transitions, so it'll be inherited by whatever successor theories there might be. So a variety of different realist positions involve kind of staking out claims about how things are going to go in the future, I think. And I think the same is true for some varieties of anti-realism, and thinking now especially of Lauden's pessimistic induction. So the claim here on the other side is that our best, most successful theories will fare poorly. Their central theoretical terms will turn out not to have referred to anything. Or they'll be superseded by theories that make sense of the world in completely different ways, sort of a Kuhnian version of this maybe. And thinking about this, I'm just struck by at least I have the intuition that non-localized bets on or against science are generally going to be riskier than localized ones. Like, prima facie, the bet that I made seems like it ought to be safer than the bets associated with this realist and anti-realist position, just because the one I made involved this kind of very narrowly circumscribed issue. One concern here is that there's a relevant difference between the two cases. This could be really important. I've been thinking a lot about this. This is one of the pieces of the argument I'm not sure is completely nailed down. Realists and anti-realists are taking existing current theories and placing bets about their fates. In my case, it was different. I wasn't talking about any particular theory or hypothesis. I was betting that we'd never be able to answer this particular question about the colors of the dinosaurs. So they're not exactly the same sort of case. In reply, I'm not sure how convincing this is, but it's a stab at a reply. if you look at it a certain way, the cases do have something in common. All three cases involve bets about future evidence. So I was betting there wouldn't be any future evidence of a certain sort. Realists and anti-realists are placing bets about kind of how future evidence that does come in will bear upon our best current theories and hypotheses. So looked at in a certain way, there's a similarity. And the question is, of course, whether that similarity is really the relevant one. So another concern about this is that I actually think this objection might be right. It might be too hasty to adopt a no betting policy on the basis of one failed bet. I mean, that's just a quick, like, conservative, risk-averse response. It just might be too quick. That might be right, but then the problem is that if you don't think the no betting policy is the way to go, then your view is going to be, well, some bets on future directions in science are sort of unwise or imprudent. Some are maybe warranted and rational and acceptable. So this is now my suggestion. I think we need some kind of more systematic way of thinking about which ones are the good ones and which ones are the ones to be avoided. And I don't have such an account. And the kind of concluding challenge I want to maybe leave everyone with or invite everyone to think about is whether realists and anti-realists might need such an account or might need to think in a more systematic way about when bets on future directions in science are justified. One final thought, one way of thinking about this argument I've just tried to sketch a little bit is it could be thought of as a kind of meta induction, like a pessimistic induction from history of failed bets against. Now it's a small sample size, right? Just one case, right? Which is related to that previous objection I mentioned. But that's sort of one I think kind of interesting way to think about the nature of the argument. So with that, just to rehearse the main take-home messages, I think the failed bet against dinosaur science, as embarrassing as it is, doesn't actually matter that much to the debate that Cleland and I were having. But that's because I think there was this other problem with the way the debate was framed in the first place. More interestingly, maybe, I do think this example should make realists and anti-realists both a little bit more cautious about placing bets on the fates of current scientific theories. Okay, so thanks very much.